Okay, now what we're going to do is talk about the neurophysiology of primary motor cortex. What does the activity of neurons in this area correlate with in terms of behavior? What does it represent? And there's some overriding themes we'll be discussing here. One is that, first of all, in cortex, because there are so many different neurons and because there's so many different aspects of movement control here, that we can't delineate simple circuits the way we could in spinal cord and even in some situations in brainstem. Things here are a lot more complicated. Okay, and there's going to be a great diversity of different responses, you'll see. And another point is that a lot is still unknown. It's still a very active area of interest. So what I'm going to be doing is giving you not really a full-blown comprehensive picture of how cortex controls behavior, but just some examples of experiments. But there's a lot that I'm not going to be able to talk about and a lot that is still unknown. Okay, so one aspect here is just the great diversity in terms of what these neurons can represent in terms of behavior. So first of all, you will see activity in primary motor cortex, which will resemble that you see for activity in spinal cord. Okay, so for example, for some neurons you'll see a relationship between neural activity and force. So in this case, what's happening is you'll have a monkey perform a task in which the monkey has to exert a certain amount of torque, and you'll be measuring from neurons and just looking at their firing frequency. How many action potentials do they fire per second? And you'll get little graphs like this. Each line represents a graph obtained with a curve fit obtained for an individual neuron. So there's many different neurons that were analyzed here, and they'll get several data points for each neuron to construct these graphs. So notice you have these sort of more or less monotonic relationships. Monotonic meaning that that this curve just goes up. For higher torques, higher amounts of force produced, there's greater activity than lower amounts. Notice there's also an element of recruitment here. Like for example, some of these neurons will be very low and then suddenly it'll start taking off at a particular torque. Okay, just like you also see for certain motor neurons in the spinal cord. Okay? But what you're also seeing here is what we could call non-monotonic relationships, instances where you can actually have more firing for less force. So in this experiment, we took a neuron, and this actually, when you're seeing this CM, this is what's referred to as a cortical motor neuron, a neuron which with various methods has been identified as a neuron which projects directly from the cortex to motor neurons in the spinal cord. So this is a neuron that's only one synapse away from the muscle, and I can talk later about how you're able to identify such neurons even in a live behaving creature. So you don't have to kill the animal to demonstrate that what cortical motor neurons are. I can talk about this in class a little bit. So what's happening here is that you're recording from this neuron, and what you're doing is you're having the monkey perform two different tasks. In one task, it's got these levers, or these little bars attached with springs, and what that monkey has to do is grab these bars and pull them together. There'll be some tension trying to pull these bars off to the sides here, but the monkey has to pull it together to a particular distance. Okay, that's task one. And the second task, it's similar muscles, similar hand muscles and upper arm and lower arm muscles the monkey has to use. But in this case, the monkey simply has to grab on a particular bar, okay, that's measuring the amount of force it's producing. So notice here that in this task, he's got to produce probably lower amounts of force, but greater precision. In this task here, he's got to perform a task with greater amounts of force, but less precision. And here's what we're seeing here. We're seeing both the EMG of the muscle, again reflecting the action potentials traveling on muscle, and secondly, the activity of this cortical motor neuron. So notice first of all that the EMG of the muscle is it's higher in this case when they have to produce a lot of force than less force, okay? Just as I described. So clearly the muscle is producing more force here than here. But now look at the activity. There's a large amount of activity for when the monkey has to make this precision grip, but basically no activity when the monkey has to make the power grip. And what's interesting here, again, this is a neuron that actually is projecting directly to motor neurons in the spinal cord. It's very interesting. Okay. Another interesting thing here. Time 0 is the point where this muscle begins to be active, the movement begins to happen. But notice you have activity happening well before that. And activity actually here, well, even before the instruction, well, I shouldn't say that, but well before the actual movement is initiated. This is referred to as preparatory activity, activity that occurs before the muscle begins to get activated, well before. And this is an indication that you can have nervous system activity in the cortex without the muscle firing at all. Okay, you'll see this very little in spinal cord, but you'll see it much more in motor cortex. Okay? And here's results of another experiment showing more abstract elements of motor control. Okay, in this task what happens is the monkey has a joystick, okay, at the center of a table he's looking down on. There are 8 lights arranged in a circular pattern here, okay, different positions relative to the joystick. And the monkey will then be instructed by presenting a light to move that joystick in one of these 8 directions, okay, to the right, left, up, down, or basically away from the monkey, towards the monkey, and in various diagonal directions. Okay. What's happening here is that there's many different types of muscles that can be used. The biceps, the triceps, various shoulder muscles, just depending on what the direction is going on. So there's many muscles that are being activated here. But what's really distinctive of each type of movement then is the direction that the movement is made in. Okay. Now what we're doing is looking at recordings of a neuron performed while the monkey was performing movements in these different directions. What you're seeing here is that each line represents a particular trial, a particular instance when the monkey is instructed to make a movement. Okay, so for each of these, there's basically 5 trials, 1, 2, 3, 4, 5. And each little black mark here, this little black vertical line, is an action potential. Okay, so each one of these represents that an action potential was made. Time 0 here is the time at which the movement starts. Okay, and finally what we're seeing here is a plot for movements in each of these different 8 directions here, going from 90 degrees, which is basically directly straight away from the monkey, 0 degrees to the right, 180 to the left, 270 a movement towards the monkey. Okay, and what you can see here is that this neuron is active now for a wide range of directions, but what seems to be important here is the direction that the monkey is making the movement. Okay, so you see activity. There's activity even well before the movement, but around the time when the monkey decides to make the movement, that neural activity picks up. The action potential firing rate goes much higher, but you'll see it's actually happening for many different movement directions. Okay. There's certain movement directions in which there's clearly a monkey motor movement, but no activity or no increase in activity at all. Notice something else that's interesting here. For a certain range of movements, you actually are accompanied by a drop in activity, where activity actually goes down. Okay? Now this graph here is basically summarizing what's happening. It's plotting the average number of impulses or action potentials per second as a function of the direction of this movement. Okay, so you can clearly see the peak here, whatever, around 150 or so. Okay, that's corresponding to a direction like about this. So you have a lot of activity here, much less activity for movements far away. But notice what we refer to as the tuning. In other words, the dependence of this activity, the sensitivity of this activity to direction is very broad. Okay, there's basically a very wide range of activities, of directions for which this neuron will fire. Okay? So this is indicating that for some neurons, as I showed a few slides ago, they'll fire in corresponding to increases in force. Others will fire for precise movements, but not very crude, forceful movements. other neurons will fire based on movement direction, okay? So let's now, again, I can't exhaustively talk about all the different experiments that have been done in motor cortex, but from the experiments that have been done, we can outline certain principles of the neurophysiological principles of these primary motor cortex neurons. Okay, so, and particularly there's distinctions here between neurons here in cortex and neurons in spinal cord. So, first of all, many neurons can be active well before that there is a movement, well before the movement starts. Many neurons will not be active when there is a movement, okay? Some neurons will have greater activity when the muscle produces less force. These are neurons that may participate in de-recruitment, helping to stop neural activity, prevent, possibly through inhibitory interneurons in the spinal cord, help prevent neurons in the spinal cord from firing, okay? And in general, you see a lot of diversity here. You have neurons that will code for force, neurons that code for direction. You'll have neurons that code for preparatory activity. It's also been found that some neurons will correlate with joint position, joint velocity, etc. So there's a lot of diversity here. And now what does this all mean? And this is going to be a bit of a segue to discussing the premotor cortex, which we'll do in the next lecture. What we have to think about here is what we could call a voluntary motor control hierarchy, okay? That starts with thinking about, ultimately, in the end, the activation of particular muscles. Okay, but we know that a particular movement is not just the activate, at least a goal-directed movement. Let's say reaching out and pointing to one of you, who's raising your hands to answer a question, is much more than just the activation of a single muscle. For that to happen, you're going to have to activate individual motor units in that muscle. Okay, then you're going to have to do that. You're going to have to activate joints, but not necessarily just one joint. It can be multiple joints, okay? Such that ultimately, in the end, what's really key in the end to making this is just the change in the limb position of at least the change in the position of the arm, such as if you're doing a reach, or in both the arm and the fingers, if let's say you're going to go and grab something, okay, or point to something. So there's a hierarchy here that overall movement is going to be a whole complicated set of movements around particular joints, each of which then can involve a combination of different muscle activity. So it could be both agonists and antagonists, but in certain cases even more than just two muscles. Okay, if we're talking about the upper shoulder or the neck, etc. So there's got to be what we call a hierarchy of motor system of movement production, starting at a high level and going down to a low level. And what you see then is that neurons in primary motor cortex can represent things at all these different levels. What we're going to do next, talking about premotor cortex, is talk about levels that are even beyond, just in a sense, beyond the movement itself. And when we come back, we'll talk about that. Okay? Sorry, this is just to point out that when you're changing limb position, you're having synergies between muscles and joints. Okay, come back, we'll talk about premotor cortex.